All right, guys, we got the energy chapter. Let me move this. These are the equations, and we'll talk about these as we go through the slides. Couple things. They're also on the equation sheet. They're on the note sheet. You can always write them down here. You can pause this and write them down. This is what the equation should look like. There are variations of it, and I'm just going to kick it back to you if you send me the variations. So you got to use what we're discussing in class, same as always. And then just the little side note here: energy is what powers everything, right? Name anything, and you got some kind of energy equation that goes for it. So understanding that's going to help us. We're going to talk about how it's transformed, used. Now, some of this you've seen since middle school, maybe even elementary school, to be honest with you. We're going to talk about it in a little more detail than what you remember, but it's still the same idea. A couple things about the equation. So this first equation under the work and power here, work is the net force, so it's just the total force. We don't have to go back to F equals ma. We're just going to get the total force, and then D is going to be the displacement. Cosine theta is only if you're pushing at an angle, and we're not going to do it. We'll just push straight on or straight up. W equals delta E. We'll talk about again another cosine theta down here. We're gonna gloss over those and just do straight pushes. Kinetic energy we'll talk about. Now potential energy, there are two equations. The one of them we'll talk about. Let's just get into it. But these are the equations. Um, so the introduction here. Sorry, I don't have this set up in a video for you, but uh, and we're gonna gloss over my near death experience. It's well, here I might as well tell you. What must be done to lift yourself to the ceiling? So I got a little pulley system, and you pull yourself up to the ceiling. And so then what do you have to do to lift yourself to the ceiling? Well, you got to pull down, right? There's a force, and when you pull down, you go up. So there's a displacement. Now the pulley system redistributes it, so your force is up and your displacement's up. And as you go higher, you're gaining energy, right? You're gaining potential energy. So the silly story, real quick, is we used to stand on it, and you would raise yourself while standing. But that I did it one time, and I wasn't paying attention, and my feet flipped out from underneath me, and the rope just gave, smashed down on my back, got the wind knocked out of me. I knew I wasn't dying. I knew it was the wind knocked out of me, but it was still uh, a little traumatizing. All right, so what is energy? It's just what I just said, right? It's the ability to push something over a displacement, and we call that work. And we'll like it says there, we'll do a future discussion on work. Right now, we're gonna do the two types of energy real quick. But there's potential stored, and kinetic is motion. Uh, any motion, not now. Kinetic friction was just sliding. Kinetic motion, though, kinetic energy is everything. And then units we're gonna use is joules, and then a joule. So here, if we go I have this out of order, kind of. If we do so what are the units for force? Well, here, let's go through it. So a joule is the units of force times the units of meters. So you can also say Newton meter. You'll see Newton meter as an option. For me, I think I just usually use joules, but Newton meter is also acceptable. Now, kilograms. Now, where does that unit come from? Well, right? It's force times displacement. So it's newtons times meters. And then we know newtons are kilograms meters per second squared, like it says here. And then if you multiply by a meter, you get kilograms meters squared per second squared. But that is a mouthful. Just like force units are kilograms meters per second squared, like nobody says that. So we named it after Joule. And then that stuff. Oh, here I gave the answer away. Now, what units? That's the metric system. What units do we use? And if you're thinking about food labels, hopefully calories pops up in your head. When we were first studying this stuff, we thought heat was its own thing. We did not realize it was a form of energy. So while studying heat, they came up with the unit called the calorie, and it is just the energy needed to raise 1 kilogram of water 1 degree Celsius. It's the energy so it's like using calories is like using miles, right? Calories and joules is like miles and kilometers. They're both measuring the same thing, right? How far for miles and kilometers, or how much energy for heat and energy. But so we stuck with calories, and then the Coke labels here. I just thought it was interesting. This is ours, right? 140 calories, and then if you're looking at a European version, 180 kilojoules. So it's 180,000 joules 4,186 joules is 1 calorie. Now they do have 42 kilocalories, right? That's almost like ours. Um, Although I should look, what's this can size? It doesn't matter. Here, we're wasting time. Anyway, you get the idea. They use the metric system. We use our system. The lab, real quick, is relatively straightforward. It shouldn't. Hopefully, it doesn't bog you down too long. It's the same old questions, but the question is, how does a spring know what you weigh? When you step on a scale, you compress a spring. How does that spring know what you weigh? And so you're doing a simulation one, so you don't have to worry about overstretching it. And then make sure on the lab that you click the lab one. If you do the intro, it's not going to match my directions. You have to click on the lab tab to get the lab. See bottom of blah blah blah. Oh, you're only measuring the displacement, so it's not the length of the length of the spring does not matter. It's just the displacement of the spring. That's the lab. Do the notes first, but then you're going to go back to the lab. But there's different forms of stored energy: chemical energy, food, batteries. That's chemistry. We're not going to cover that. Nuclear energy is a physics 2. If you have a physics 2 at your school, like I highly encourage you to take it. There's where you get into nuclear energy. So we're going to focus on the more mechanical stuff. So spring energy and gravitational. And then the equations for gravitational, there are two of them. We're just going to focus on this first one, the U equals mgh. Now you would think gravitational potential energy, a lot of books use PE. A lot of stuff online is going to use PE. We're using U. The variable for potential energy, any potential energy is U. Some books still stuck to the old PE. I'm going to send it back to you. It's not a variable we use anymore. And then M is mass, that's the same old. G is gravity, that's the same old, except it's positive 9.8. And then H, finally we got an H. I know some of you have been using H for dy. They save the H for potential energy because it has nothing to do. Energy doesn't have anything to do with direction. So G is here, this equation, the U equals mgh, only works when you're near the surface of the Earth. So a few hundred miles from the surface, we're good. You start going into the thousands of miles, then you got to use this other equation, which I'll talk about in 1 second here. So as long as you're near the Earth's surface, it's 9.8 meters per second squared. H is the distance from the surface. And then H would only be negative. If they tell you the surface is here and you're down here, then yeah, that's a negative. Right? Here's 0, then you're down here, it's negative. But it's not a directional thing, it's just you owe money. Which is why this equation over here is negative. The way we set up, this is for if you're escaping the planet. If you're trying to break free of Earth's gravity, then you got to use this one. And then why it's a negative is because you got to give up that energy to escape our planet. And then G's, it's not 9.8. This is a capital G. It's 6.67 times 10 to the negative 11. It's tiny. So you take two masses, M1, M2, and divide by their R. So if you did it between you and the person next to you or whoever's nearest to you, it wouldn't be much energy. Your two masses don't account for much, and then the distance between you wouldn't do much, and then G is even smaller, 6.67 times 10 to the negative 11. It might as well be 0. But if you do it for a planet, then it gets big, right? You put a planet's mass here, and you can put your mass, and then how far you are is how far you are from the center. Anyway, you can calculate the gravitational potential energy between you and the center of the planet. But it's a limit. It's one of those limit equations. So is the radius, as you get further from a source, the potential energy plummets to 0. It never hits 0, but it approaches 0. It's a limit. And all right, one more form of potential energy is spring energy. And then this is what you're going to do in the lab. Although the lab doesn't ask you about the stored energy, it just asks you about the spring constant. So in the lab, you're going to figure out what the spring constant is for a silly simulated spring. And then that'll help you answer how do springs know how much you weigh? It has something to do with the spring constant we call K. And it's a lowercase k. Capital K is going to be kinetic friction. Nope, sorry, not kinetic friction, kinetic energy. Lowercase k is the spring constant. And then the displacement, instead of using d or dx, they went with x. So now if you've been using x, it's okay to use for this stuff. So u is potential energy. With the subscript s, it's telling you it's a spring, and then it's 1/2 the spring constant times how far you stretch it or compress it squared. And then F is a negative kx. That equation is negative. That's going to tell you how much force is in the spring. So if you've ever taken a spring or a rubber band or those like color coded workout bands and you stretch it and you feel that tension trying to pull you back in, that's the force. It's negative because you're pulling this way, but the thing wants to pull you this way. So because you're pulling opposite of the way the force is applied, we make the equation negative. And then K is just the spring constant in the X. And then, all right, last form of energy for us, kinetic energy is all your motion energy. So radiant energy, we might get to light. It just depends on how the semester unfolds. It's definitely a physics 2 topic. Thermal energy is definitely a physics 2 topic. Again, we might touch on some of this stuff. It just depends on time. Sound energy is also a physics 2 topic. But if actually that one we might get to. It just depends on the timing of the semester. And then motion energy is what we're going to focus on right now. All right, so a video I can't show you, but here we'll talk about it. Are two identical cars in a head-on collision? If you look it up, it's Mythbusters, and then type in this description. Actually, if you type in this description in Google, the video will probably pop up. But are two identical cars in a head-on collision, each going 50 miles per hour? So two cars, head-on collision, 50 miles an hour. Is that the same as one car going 100 miles per hour into the wall? So the question is, two cars coming at each other at 50, is that the same as one car going into a wall at 100? Oh, sorry. It is a Mythbusters video, but the YouTube will flag me if I play it. All right, so let's see if this pen lets me write. All right, so there's two ways. Well, here we'll do the first way first, because this is usually what pops in your head first. Is that when we talked about relative motion from the very beginning, the first few weeks. If I'm coming at you at 50, you're coming at me at 50. We would be coming at each other at 100 miles an hour. As long as we're in our independent cars, I can argue that you're going 100 and I'm going 0, and then you're coming at me. You could also argue the same. I'm going 100 and you're going 0, and we're coming at each other this way. That is fine, and physics accounts for both situations where we could both be moving at 50 or 0, 100. It's all the same to physics, right? Because there is no difference between being at rest and being in constant motion. You don't feel any difference. The problem is, in this case, you're going to have a collision. You're going to have a car crash, and then you're going to know. You're going to know you're the one accelerating. You're going to feel that. So relative motion does not apply here. Now, the kinetic energy. So I'm going to go through this real quick. If I want the kinetic energy, this is the factor of change thing that we've done. The 1/2 is a constant. Oh, that's going to be real fun. Sorry, guys, that K just disappeared real fast. Yeah, I'm going to do this real quick. This is, here, I'll do it over here. This is going to become, if you remember the factor of change, anything that doesn't change becomes a 1. So they cancel out. They divide out. I shouldn't say they cancel. They divide out. And so all you're left with is V, which is doubled, which is 2 squared. So let's just say, hypothetically, the two cars going 50 miles an hour. Let's just say they have 100 joules each of energy. Yeah, let's just do 100. 100. I have 100 joules. You have 100 joules. We collide into each other. That's 200 joules of energy that we have. Now there's two of us, and we're in identical cars, so we will split that energy, and then we have 100 and 100. So two cars coming at each other at 50, when they collide into each other, is the same thing as a car going into the wall at 50, not 100. Here's what happens. When you go 100, that's doubling your speed. That's quadrupling. That's multiplying your energy by 4. So you go, if originally at 50 you had 100 joules of energy, if you go 100 miles an hour, you're going to have 400 joules of energy, which is 4 times as much energy as you do with at the 50 mile per hour crash. And that is why 50 miles per hour, you could walk away from that. 100 miles per hour, that's 4 times the amount of energy. Then we're taking chances. You're definitely taking chances. But that's the factor. There'll be some factor of change questions. Message me if those aren't making sense. I can show you the long way. I think I showed you the long way when we first introduced it, but it's been a few weeks. All right, so, a couple more things here. Work and energy. So here's what I referenced back in that first part. Work is done on an object when applied force is in the same direction as the displacement. So when you do work on something, the displacement has to be in the same direction as the force. So I don't have a basketball. Sorry. Here we got Transformer guy, Optimus. I'm holding him, right? I'm pushing up on him. He's not displacing though. So did I do any work on him? No. Is my arm going to get tired eventually? Yes. So internally, my cells are doing work. My muscles are doing work. They're pushing and displacing internally. But on the transform itself, nothing's happening. Now, if I lift this guy, right, I'm pushing up and his displacement's up. I definitely did. I did work on this guy. And what did he gain? He gained potential energy. He gained gravitational potential energy. So there's two ways to answer the question. Did you do work on this transformer? There's two ways. Did you push up and did he displace up? Yes. Then you did work on him. The other way is, did he gain energy? Yes, he gained gravitational potential. So there's a yes. Now lowering him though, I'm pushing up still, but the displacement's down. So I didn't do work on him, right? He pushed me down and I displaced down. So he did work on me, but I did not do any work on this transformer. He actually lost energy, which, so if you do the change in energy part of it, he lost energy, right? His change in energy was negative. Um, where does that energy go? It has to go somewhere. When I lift him up, he gains gravitational potential energy. When I lower him down, where'd that gravitational potential energy go? It can't just dissipate out into, I mean, it does dissipate out, but where did it go? And it goes into me as heat. That sounds weird, but it goes into me as heat. Now carrying this thing, if I'm just, well, here that's tricky because I gotta walk. If I'm moving with him and not actually I'm just moving, walking across the room with him, um, I'm pushing up, but his displacement's to the right, so no energy, no work done on him. Now throwing him, if I threw it at you, right, my force is towards you, the displacement is towards you, that's a gain. Now he gains kinetic energy. So that's work. The cosine, like I said, this is what it would look like. We're just gonna always push horizontally or vertically, and then we won't have to worry about the cosine. And then the units for work, kind of already talked about this, but well, we talked about energy in general. Work is just how you change energy. So it's force times displacement, so it's a Newton meter. And we know Newton meters are joules. So they have the same units. All right, the class kick problems you're gonna come to, there's two there's three ed puzzles. One of them just kind of one of them is somebody else explaining the work energy theorem with better examples, like actual video examples for you. The other two are me doing the problem, so make sure you look over those and see if they make sense. It's not This chapter's not awful. It's not like the fourth chapter. That one takes some processing power. This one will take some thought, but not like forces. Uh, Here's another demo, guys. So here, what we usually do is we time. There's a little pulley system in the room, and we time each other to see who can get to the ceiling first. Um, I'm just gonna give you numbers because this thing's. Let's just say we both go about a meter. So we're lifting force is 100 and 100. Let's just say it's 100. You're 100 newtons of force and I'm 100 newtons of force. So how much work did we do? It's just 100 times 1, which is 100. So we both did 100 joules of work. Here's where things can differ. Let's say I took half the time. Like let's say I was twice as quick as you are. You can argue the other way. You're probably twice as quick as I am. Let's do it that way. You guys are probably gonna beat me. So who did the most work? Well, we did the same amount of work. We got to the same because we both lifted 100 newtons of force. So we did the same amount of work. Who exerted the most amount of energy? Well, work is a change in energy. So since we did the same amount of work, we used the same amount of energy. The last thing there is, well, what about the time? How does the time work in? Uh, why are you more tired if you did it in half the time? Uh, it's not that you exerted more energy, it's that you exerted more energy per second. So who exerted the most amount of energy per second would be you, right? You did more because you did it quicker than me, right? Your t is smaller than mine. I took 4 seconds, you took 2 seconds. Well, 100 divided by 4 is 25. 100 divided by 2 is 50. You did 50 joules every second, and I only did 25 joules every second. That is what we call power. So does the amount of work differ between walking up a flight of stairs or running up a flight of stairs and coming to a stop? No. It doesn't matter if you walk or run up a flight of stairs. We're both going to end up at the same elevation, and we're both going to use the same amount of. I'm sorry, not you and me. It's just you. You walking versus you running will be the same. Um, so why are you more tired when you run up a flight of stairs? It's because you exerted more power. You consumed the same amount of energy, but you did it more per second. And then work is force times displacement. Displacement over time is velocity. So you can also find this with force times velocity. I don't know that I did that to you. Yeah, I'm sure it's possible to do it, but if you just do work over time, like you'll get, oh, power. Capital P is power. Lowercase p is something else. There's no way I'm going to tell if it's a lowercase p or capital P, but just be cautious. Lowercase p is going to mean something next chapter, next week. And then the cosine theta again is if you're pushing at an angle, and we're going to not to push at angles. All right, couple. I keep saying a couple more. We're getting there. Power, because it's a joule per second, we call that a watt. You can also use joules per second, but that's what we call watts, which most of you have probably heard watts with light bulbs. And I'm just gonna do this real quick. Let's just say incandescent bulbs are the filament ones that get really crazy hot. Halogen also have filament, also get crazy hot, but they last a little longer. They're a little more efficient because there's a gas in there. Halogen. I think the gas is actually halogen. They've started phasing these bulbs out because they're not efficient. The 100 watts, 72 watts, every second, right? That's 100 joules every second of energy that you're consuming. And most of it goes away as heat. So then they came up with compact fluorescents, which are much more efficient, right? Now you're using 23 joules per second. They last longer, 6 to 10 years. Regardless, though, that's still a lot of energy as heat. So then now we got LEDs. Most likely, most of the bulbs you have around your house are LEDs. You can touch them, right? They could be on for days, and you can touch them, and they're warm, but they're never hot. Like they're never scalding hot. They last a lot longer, depending on quality, but they should be lasting longer. And then it's 20 joules every second. So instead of using 100 joules every second, like we did 20, 30 years ago, now we're using 20 joules per second and we're getting just as bright light. So how do you know how bright a light is? Then, oh, sorry, my bubble's in the way. You got lumens off to the side now. So instead of just looking at wattage, you look at lumens. So if I want something really bright, I go 1600 lumens and I go lowest wattage, right? I don't want to spend a ton of money on this light bulb. And then so that's wattage. What are the power units for a car? I think most of you know this. It's horsepower. So when they first came up with the engine, they were trying to sell it, right? They would say, "I have a 750-watt engine," and everybody that doesn't mean anything to anybody because they're all using horses. So then they did some experiments and measured how much wattage a horse can do, right? You can just time it, right? Power equals work over time. So they can measure that force could just be a weight. They lifted a weight, a certain displacement, and they timed it. That like I just explained. Sorry, I couldn't show you, but that I just explained. And you got the power for a horse. It turns out 1 horsepower is about 750 watts. And so then they started selling horsepower for engines. And now, like if you have a lawnmower, it's the equivalent of 2, 3, 4 horsepower. Your car could be up in the 200 horsepowers, and that's literally the equivalent of 200 horses. Like it's silly, but it's literal. Um, Problems. Your system requires the least amount of effort to lift the weight. Oh, here. Energy is the chapter that we would do simple machines. I feel like you've done a lot of that in elementary and middle school, so I kind of just gloss over it. Um, but there is an energy problem. I don't know that it's problem 4 for you guys. Here, we'll talk about it real quick, and then either you'll see it or you won't see it. But if I pull down with 100 with one pulley, it pulls back with 100. If I have a double pulley system, I can get 50 in each rope, still get my 100 up, right? I'm trying to lift something. All I have to apply is 50. Now, and then I'm only raising this thing 10 centimeters, 10 centimeters. How much rope did I have to pull here? 10 centimeters. How much rope did I have to pull here? 20 centimeters. Because you have the force, you have to double the distance to keep that energy conserved. You can't just lose energy or gain energy. So yes, it's easier, but you got to pull more rope. So then do 3 pulleys. It drops it down to about 33 newtons. But to lift that thing the same height, 10 centimeters, I got to pull 30 centimeters of rope. And then you get the idea. 4 pulleys, I can distribute 25 over each rope. So um, that 100 that I'm trying to lift gets split evenly between those 4 ropes, and then I only have to pull with 25. But because it's split by 4, I got to pull 4 times as much rope. And then symmetry and conservation. So this energy, I think you've heard this before too. Energy is conserved. You can't what you started with is what you end with. Like that is a physics like universal fact. And it comes from for a long time we didn't know where it came from. And then when did she so 1900s this Emmy Noether realized uh, that if time because time is symmetrical I don't even know this. There's a mathematical way that you can take the idea that time is symmetrical and naturally out pops this idea of conservation of energy, which we're going to talk about in a second here. But the idea is that if the laws of physics don't change over time, so that whatever the universe said yesterday is whatever the universe says today, then energy is going to be conserved, is the idea. And then this is a little bit about it. She refused to accept that women couldn't pursue this. This is not 1900s, right? So anyway, she pushed to be accepted in academics, and she did have to teach in secret in that. You can read over this, but this is a quote from Einstein, just in the she was the most significant creative mathematical genius thus far. It's like he was giving her props. The conservation of energy. So here's what comes out of that. Now we knew conservation of energy before her, but she just proved you like why it is. We didn't know why it was conserved. She was able to prove why it is, and it's called abstract algebra, guys. That's it's I don't even know that I took abstract algebra, but it exists. Initial energy equals final energy is conservation. So if you've seen the swinging bowling ball thing, it's a cool video to look up. But you put a bowling ball up to your face and let go, it comes out, right? That potential energy is going to swing into kinetic. At the bottom, it has all kinetic, and then it's going to pop up to all potential. And it's just going to swing back, swing back, swing back. Um, and then pretty much shows, but every time it swings, it gets a little less higher. And so it is losing some energy to friction, the air resistance, and stuff like that. Balls do the same thing. When you drop a ball, it never the most it could bounce is back up to where you started. If all you give it is 10 joules, it's only going to come up to 10 joules. But half the time, it only goes like half the way up. You drop it from your head level, and maybe it gets to your chest. Maybe if it's a decent bouncy ball, but where'd all that energy go? Well, it heated up the ball, it hit the ground, it made a sound probably when it bounced. So we're looking when we talk about conservation of energy, EI equals EF. We're not going to account for that the stuff lost to friction, to heat. We're just going to look at, let's just say I have a ball up here. How fast is it going right before it hits the ground? Well, if this is all gravitational, this is all kinetic. And those have to equal each other. Now, after it hits the ground, then some of that energy gets transferred to the ground. And then we're going into into more details. All right. Energy conservation practice. I think we're going to skip that. Sorry, guys, this isn't us. Desmos. All right. That is it, guys.